Okay, so obviously we're going on to our next unit here, 6.3, which is on this concept of heat transfer and thermal equilibrium. Okay, and again, we already tiptoed around this idea of heat transfer. We just haven't talked about that back half, which is thermal equilibrium. Okay, but basically energy transfer. Okay, energy transfer happens all the time because again, energy is not created or destroyed. It has to go from one thing to the other. Okay, and yesterday or 2 days ago, we talked about systems versus surroundings. Okay, and if the energy transfers from the system to the surroundings, that makes it an exothermic reaction. And if it transfers from the surroundings to the system, that makes it an endothermic reaction. Okay, but this one's not even going that in depth. This one's just straight up talking about energy transfer. Okay, and basically that is talking today about heat specifically. Okay, and if we look at this first bullet point, it says energy as heat transfers spontaneously from hotter objects to colder objects. Okay, so again, the word spontaneously means like without any requirements. Okay, it's just going to happen. All right, so again, something hot is going to transfer to something that is cold. Okay, so it's not the other way around, cold going to hot, it is hot going to cold. All right, so if you think about a hot beverage and you put an ice cube in there, what's actually happening is your hot beverage is transferring its heat and it's warming up that ice cube. Okay, so it's not that the ice cube is cooling down, it's that the liquid is sending its heat or removing its heat by giving it to the ice cube. Okay, and what happens is that heat transfer keeps going, right, until everything is at the same temperature. Okay, we're going to melt those ice cubes until they're the same temperature as the liquid. Okay, and again, as we mentioned, we can't actually measure energy, okay? But we can measure temperature. And as we know, kinetic energy has a relationship to temperature. So what we can do is, again, when we measure the temperature and the temperature stays the same, we can say, okay, the average kinetic energy is about the same as well, okay? And this heat transfer back and forth or you know, until everything gets to the same temperature, once it's all at the same temperature, that's called equilibrium. Okay, again, if you look at the word equilibrium, it kind of has the word equal in there. So again, maybe a mnemonic device, I think is what they're called, right? To help you memorize or remember. Okay, so equilibrium means that everything is equal. Okay, and thermal means heat. So we have equal amounts of heat throughout our entire universe, the system and the surroundings. Okay, any questions so far on energy transfer? Awesome. So this is a really nice diagram. I think it makes it kind of obvious as to what's happening. Okay, so block A is red, meaning it's hot. Block B is cold. Okay, when they touch or they combined, we have a heat flow. And again, the heat flow always goes from the hotter object to the colder object. Okay, and this is going to keep transferring heat, transfer heat until they're both at some same temperature. Okay. And again, the amount of heat that is released by one object is equal to the amount of heat absorbed by the other object. Okay. So they will be equal. All right. Again, we always assume, I know you might have talked about in physics, like loss of things or not perfect collisions. We always assume in chemistry that everything is perfect. Okay. So on these two links here, okay, we're not going to spend a whole ton of time, but if you are somebody who has trouble visualizing what this looks like, these little two PhET simulators are actually really nice. Okay, so for example, if we just look at something really basic for this intro here, okay, you can take a thermometer and put it in your water. Okay, we can heat our water up. And again, I know these are kind of silly, but they are really nice visualizations. Okay, so we've heated the water up, and if we look at our brick's not very warm. If we put our brick inside the water, the temperatures even out. Okay, the water gave the heat to the brick, lowering that temperature, but raising the temperature of the brick. Okay, and that will happen with iron, that would happen with olive oil. So again, if we take our thermometer, put it in the olive oil, put this one here to the iron, If we heat the iron up, okay, awesome, and we dump it in the olive oil, obviously they're going to balance out to the same temperature. Okay, and again, once they're at the same temperature, they are equal temperatures, meaning they are at equilibrium. Okay, the same thing works for a system. Okay, so this person is pedaling a bike that is transferring their energy. The energy gets transferred to the light bulb. That is then going out as light. Okay, so again, energy has to be used. And then obviously this person's starting to get tired, and then it says, feed me, right? They need energy. Okay, so again, both really good simulations. The second one on this page, if you want to, again, explore it a little bit more, is talking about properties of gas. Okay, so we did talk about the ideal gas law and non-ideal gas laws in one of our earlier units. Okay, but both or all of these are really, really good to look at. So again, for example, if we look at the energy one, okay, if we pump in some gas particles, okay, we can see over here the average speed. Okay, and as we know, right, the speed of the particles makes that distribution. Okay, it makes that distribution. Then if I heat the particles up, we can see that they're going to start moving a little bit faster. Okay, and in the left-hand corner, you can see that my speed has flattened out a little bit, and it's now shifting towards the right. Okay, if I cool it down, obviously the particles then start to slow down, and my distribution curve in that left-hand box that says speed now shifts back to the left and goes higher. Okay, then if I want to add in some lighter particles, right, lighter particles, even though they're at the same temperature, they should be moving faster because kinetic energy is equal to 1/2 mv squared. So they're both at the same temperature, but the smaller particles can move faster. Okay, so again, really nice simulations to play around with and to help you visualize. And again, there's 3 other options to look at with the gases. So again, if you want, those are there for you to take some time to explore those. Okay. But oh, perfect. Okay. So again, with the energy transfer, we keep going back to these Maxwell-Boltzmann distribution curves. Okay. And again, what these curves show, just like that simulation is it doesn't change the number of particles. Okay. There's still, we assume, 100 particles in the red, in the green, and in the blue. What just happens is again, as we increase our speed or our velocity, right, we shift that graph to the right, it now flattens down. Okay. But if I were to integrate or take the area under both of these curves or all 3 of these curves, they would be the exact same. Okay. So again, we just know that as we speed up, or sorry, as we increase our temperature, our particles speed up, and that shifts these graphs to the right. Okay. Again, as we slow down, right, that would be because of our temperature. All right. So, I mean, that's pretty much it with this unit. Okay. It's pretty short, sweet, and to the point. Okay. Energy transfers from hot things to cold things until we are at an equilibrium or an even temperature. Okay. So if we look at this first question here, again, you can see, or hopefully we're starting to pick up on the fact of whenever something's a really easy concept, like physical versus chemical changes, or like this one, transferring heat from one thing to another, the questions get a lot more wordy, okay? Because the difficulty in this problem is not the concept of heat transfer, it's do we understand what's going on, okay? So again, in this one here, if it helps, draw yourself a picture, okay? I'm really obviously big on pictures because I think it helps you visualize. For example, it says a piece of iron is at 25 degrees Celsius, is placed into water that's at 75, okay? In an insulated container. So basically like a coffee cup. All right. So water is hotter than iron. A student predicts that when thermal equilibrium is reached, the iron atoms, being more massive than the water molecules, will have a higher average kinetic energy than the water molecules. Which of the following best explains why the student's prediction is incorrect? Well, average kinetic energy. Okay, average kinetic energy is based on temperature. Okay, it's based on temperature. All right, so at equilibrium, both of these will have the same temperature. Okay, and it doesn't really matter what that is because we're not being asked, but somewhere between 75 and 25. Okay, so at thermal equilibrium, the average kinetic energy of the iron atoms cannot be greater than that of the water molecules. Okay, why? Because they're going to be the same, right? Because kinetic energy is similar or related to temperature. Okay, so it's just D there. Okay, it's just option D. Thermal equilibrium means they must be at the same temperature. Temperature is synonymous with kinetic energy, therefore it cannot be different. Okay. This one, practice problem 2. If we look at two Boltzmann distribution graphs, you've got graph 1 and graph 2. Obviously, graph 1 is a little bit higher and shifted to the left. Okay, graph 2 is a little bit lower and shifted to the right. Okay, so it says the graph shows the Maxwell-Boltzmann distribution for a sample of argon. Graph 1 shows the distribution of particles at 300 and then 600. So again, we could have known that relatively just by looking at the graphs. Okay, a student predicts that if the samples are combined in an insulated container and the thermal equilibrium is attained, that the most probable particle energy will be between the most probable energy in graph 1 and the most probable in graph 2. Which of the following justifies the student's claim? Okay, so lots of information there. Basically, though, we're looking at thermal equilibrium. Okay, that's the key there. Thermal equilibrium is attained. Okay, so that arrow is not even well defined of if it's to C or to D. So let's look at both of the answer choices. Okay, if we look at D, it says when the samples are combined, the gas particles will collide with one another, with the net effect being that the energy will be transferred from the most energetic particles to the less energetic particles until a new distribution of energies is achieved between 300 and 600. Okay, well, that sounds pretty good, except for nothing really. Okay, it's transferring from the more energetic, meaning the higher temperature, to the less temperature. Okay, that seems pretty good. I don't see an issue with that one. Well, let's check letter C just in case. When the samples are combined, the gas particles collide with one another until every particle in the mixture has the same kinetic energy. Okay, so right there, that's an issue. Every particle in the mixture has the same kinetic energy. Well, if we just look at graph 1, not every particle in graph 1 has the same kinetic energy. That's why it's an energy distribution. Okay, that's why it's an energy distribution. Like this might be 100 joules of energy and this might be 50. Okay, so there's always a distribution in the energies. They're not always identical. Okay, it's just the average or where they lie. So right there, answer C is incorrect. Okay, but if we keep going, it says which is between the average kinetic energy of the particles in the hotter sample and the average kinetic energy in the cooler sample. Okay, so the back half of that is not wrong, right? We're going to obviously transfer from 600 to 300, and we're going to end up somewhere in between the two. Okay, so when you go and note this up here, that arrow should be down to option D, not C. Again, what makes C wrong is that it says every particle in the mixture has the same kinetic energy. That's just impossible. Okay. And I think this is our last one here. Practice problem 3. Okay, so if we look at temperature versus time, it's clearly going down. Okay. A student adds 50 grams of liquid water at 25 degrees Celsius to an insulated container with a temperature probe. We then add 10 grams of ice at 0 degrees Celsius. We close the container and measure the temperature at different intervals. Part of the data is shown below. Okay, obviously, again, we're starting at 25 and we're going downwards. The student predicts that the temperature will continue to decrease, then level out to a constant temperature. Which of the following best explains why the student is correct? Okay, and the reason being is because, again, obviously, we're going to transfer from the hot water to the ice. But at some point, we're going to reach equilibrium. And at equilibrium, the temperature is the same. Okay, the temperature is the same and it will not change. Because again, an insulated container, okay, is again like a thermos, like a Again, a really good coffee cup. It's supposed to not let any heat out or any heat in. Okay, so once we reach that equilibrium of whatever temperature it is, maybe it's 10 degrees, okay, we are going to remain at 10 degrees until we do something else to the system. Heat it up, cool it down, remove the lid, do something, okay? So the answer is A. The H2O molecules initially in the ice and the molecules initially in the liquid will all have the same average kinetic energy, also known as temperature, okay? So that's it, okay? We are done with topic 6.3, okay? So for today, all you have is to work on your topic 6.3 practice problems, okay? Those are released right now, okay? Those will be due along with 6.1, 6.2, and tomorrow's topic of 6.4. Those will all be due at 8:30 on Monday morning, okay? Any questions for me so far? Awesome. Okay. Then that's it for our class.